This is my 16-bit floating point square root calculating machine. Look how beautiful it is. Been working on this for the past few weeks. Spent the last couple days just trying to get the timings right. Back here, especially in the adder, I was having problems with that piston getting stuck. Oh my god, it's just a nightmare. But I finally got it working. Pretty complex little machine. A lot of stuff going on in here. It's 60 by 38 blocks, which in my book is pretty compact, and in my book it's also pretty fast. Not the fastest Redstone machine I've seen by a long shot, but you know, probably one of my most proud builds to this point. Let's throw some numbers in. I'll explain how floating point works in a second, but we're going to throw in a number like 159.3. That is 1 times 2 to the 7th times 1.859. And press go. You'll see the answer will start sliding in from the right here over towards the left. Lots of stuff happening in the back here. And we have an answer, which I just happen to know is 12.62, because I already have this scripted out, but you know, so that is 1 times 2 to the 3rd times 1.578. If you don't know, floating point works a lot like scientific notation, where you have a number that starts with a fixed point. Usually in decimal it's called a decimal point, and in binary it's called a radix point. That you use the exponent to shift the place of the point along your number to end up with your final result. And of course, since this is binary, the numbers sound weird. So like 1.578 times 2 to the 3rd is 12.62. So let's throw another number in, like 2. 2 is fun to represent because it's only 1 bit is on. That means that this is an exponent of times 2 to the 1. And since our exponent is not times 2 to the negative 15, we have the 1 is implied, and all of the following bits are 0. These bits can correspond to things like 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, 2 to the negative 4. So they're all half of the value above them, which is 0.5, 0.25, 0.125, 0.0625, 0.032125, and so on. Now, since this is 16-bit floating point, you only have a 10-bit mantissa, which means that it can't represent super small numbers, or at least super precise numbers. So like the largest number that you can represent is 65,504, just because that's how many bits there are, which would be, come on, all of the bits on, except for 1, because that would not be a real number. So this one stays off because that's 2 to the 14th, which is as high, 2 to the 15th, which is as high as you can go with the 16-bit bias, or the 15 bias, and a 5-bit exponent. But anyways, we were going to do the 2. And while that's running, we'll just watch some more pretty lights happening. All right, it's done. And we have our answer of 1.415, which is 1 times 2 to the 0 times 1.415, because 2 to the 0 is 1. So that's always nice because the mantissa just lines up and you can read it directly. And of course, it's all in fractional binary with the 1 implied, so you can't read it like regular binary because it's the opposite. And converting from fractional binary to fractional decimal is a whole bag of worms. That's not the same as integers. But yeah, let's do another number. We'll do all of these bits off, which is 2 to the negative 15, and 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, which is 0.2159 times 2 to the negative 15th. Or actually, it's times 2 to the negative 14th with the 1 not implied, because that's how you get mantissas that are smaller than 1 in floating point, is by having the last one, the smallest one, be the same as the one above it, but without the 1 implied. So that's what this means. 2 to the 0, which is 1, is implied for all exponents except for times 2 to the negative 15th, in which case it's not implied. And since we have that, we will see something special happen. Up here, the exponent will change because during the process of calculating the square root, you run into leading zeros. Normally, you don't have leading zeros because the first bit is always 1, so it starts out by subtracting 1. 1 minus 1 is, it always fits into itself, but 0 minus 1 obviously doesn't work, so you have a leading 0. And those need to be accounted for. So the normal equation for figuring out the exponent of the square root of a floating point number is just half. You cut the exponent in half, and you round closer to 0 if you end up with a 0.5. And you have to account for any more leading zeros because in the final representation, the leading bit, or the first bit, has to be 1 so that it can be implied. So it basically like shifts it over, but instead of waiting to the end to shift it over, it just counts them at the beginning and continues from wherever it finds the first one and subtracts those leading zeros from the exponent. So this is times 2 to the negative 14th, or negative 15th, however you look at it. And half of 14 is 7. And there's 2 leading zeros in the result, so we have to shift over 2, so we get times 2 to the 9th. Times 1.859, there's that 1, which means, the 1 is implied, and that result converts to 0.00363. I don't know if I went over float toy, so if you want to double check any of these numbers, or if you want to play with floating point numbers yourself, you can find this cool little toy on the internet. It's on GitHub, called Float Toy. You can probably find it just by Googling. But if you want the direct link, it's http://evanw.github.io/float-toy/. And it basically just has 3 little conversion tools where it shows you the exponent, mantissa, and the result number, and then all of the zeros. You can click on each of the bits and change them 0 to 1 and play around with that, or you can enter numbers directly into the result. And it also has 16-bit, 32-bit and 64-bit, which are half precision, regular, and double precision. So yeah, that's a fun little toy. I use it a lot, especially for stuff like this. But this video is getting pretty long, so I'll probably cut it off right about here. But I just really wanted to show this off because, you know, it's one of my best builds so far, and I think it's pretty interesting. I will probably be doing a lot more stuff with floating point, so maybe expect that in the future. But yeah, bye.